A quick question about some of the extra credit work.
Yes.
So the extra credit one has the right due date. So like extra credit two, three, four, etc. They're all due like before
Last
like
semester.
January 2nd. Yeah.
Okay,
So I
so
can't
yeah, what's going on
submit
there is I
anything.
never assigned them. That's why they have the old due date. But if I go back through them, I'll look and see if I see any ones that I want to include, and if I want to include them, I'll go ahead and change the date. If I don't want to include them, I'll make them less visible. I don't know why they're visible. Well, I know why. It just automatically when you copy a course, it copies the settings that it had instead of hiding stuff. So I'll check through that, and any of those extra credits that I want you guys to do, I'll go ahead and set the dates correctly. I'll probably do that tomorrow while my
Okay.
class is taking their test.
Cool. Thank you.
All right, thanks for letting me know, and feel free to remind me if I forget, because you know me, I'm a goober, and I'll certainly forget like a goober. Anybody else have any questions? Okay, I just wanted to make an announcement, make sure everybody saw.
Yeah, thank you.
Oh yeah, go for it. But the main thing was I did finally put in all the new test banks and all that stuff. So that test should be working without having any problems loading the photos and images and stuff like that. I would like y'all to let me know if you do have any problems with the photos and images, and take a screenshot for me for best results so I can see exactly which question it is and I can figure out what bank it's coming from, that sort of thing. I'd really appreciate that. And if you'd send it to me via text, that would be best, but email will be fine as well if you don't have access to that. So, or if you just don't feel like doing it, that's understandable. I know sometimes students don't necessarily want to give their instructor their cell phone number, and that's certainly fine. I understand that some people might not want that. Anybody else have any questions before we get started?
Yeah, hey, Mr. Younger.
Yeah, Alex, go ahead.
I just wanted to confirm the face-to-face test is this Thursday during lab, right?
Yes, problem. All right. Anybody else before we get cracking?
Yeah, sorry. One more
Yeah,
quick question.
no problem.
Um, so for the final exam, I'm gonna be out of town. I'll have a room, but I emailed you a little while ago, but I just want to confirm it will be on Respondus, correct? Or I'll have the
Uh,
opportunity to.
For you guys, I believe I'm able to actually do it with your lab instructor, but I could just do it by respondus. That wouldn't necessarily be a problem. But in doing so, I would make sure I try to do that for everybody, not just for just one student, for instance, because it'd be a different due date. Let me think on that a little bit. But you're going to be out of town, right? I think I have a couple of
Yeah,
students that are going to be out of town because they're going back to college. This is Jacob. What's the first
Jacob
letter of your?
Young.
What's your last name?
Young?
Young, gotcha. You'd think I'd remember that, but no. All
All
right.
good.
Yeah, let me think on that. I might be able to just make it where my students have a deadline and they can take it because it's not really any different to take it online versus face to face, except you possibly have a different deadline. So if you can get it
Yeah.
done on the same deadline, I wouldn't have a problem with that either
Yeah,
way.
yeah, yeah. All right, cool.
Okay. All right,
All right, thank you.
no problem. All right, so we're going to get back started on chapter 10, and we were talking about section 10.5, rotational dynamics, and I'd actually done a little bit of the next section, which is calculating moment of inertia via integral methods and stuff like that. So I've got another one of those problems to solve, but I thought I'd start with solving one of the dynamics types problems, and that's example 10.10 from your textbook. I've taken the time to go ahead and write it down on my iPad. So let me go ahead and share my screen with you and then I'll read it to you. And again, if you have your ebook out, that would be best so you can make sure you understand and fully read the question as I go over them. But I think I do read them well enough that you can still do it anyways. Hopefully that comes up in a second. There it is. Okay, so example 10.10 says a 15 Newton force represented by F sub t is applied to a cord wrapped around a pulley of mass 4.00 kilograms and radius r0 equals 33.0 centimeters, figure 1022. The pulley accelerates uniformly from rest to an angular speed of 30 radians per second in 3.00 seconds. Assume there is a frictional torque sub F equals 1.10 Newton meters at the axle. Determine the moment of inertia of the pulley rotating about its center. So that's the problem. I've written down all the information on this problem in my iPad already, and I've given you a diagram, a drawing of the figure. In this case, it's a little different because the next one we're going to do, we're going to hang a 15 Newton mass from it, a 15 Newton weight from it, which is, believe it or not, very different than just applying a 15 Newton force to it. And you'll see how that's different when we do the next example. But what we'll need here, obviously, is we'll need to calculate the average acceleration, which we can assume is the constant acceleration. And we can do that by average acceleration alpha bar is equal to delta omega over delta t. And then we can use our Newton's second law for rotation. And in this case, we're talking about a reference frame in which it's not accelerating and a fixed axis. So we can use this about any point we want. We don't have to just necessarily do it about the center of mass, even though we are going to do it about the center of mass. So let's begin by calculating alpha. We can see that alpha bar is equal to delta omega over delta t. And that's omega minus omega 0 over delta t. And of course, the omega is 30.0 radians per second minus the initial omega, which is 0 radians per second. And all that is divided by 3.00 seconds. And even I can do that arithmetic. 30 divided by 3 is 10.0 radians per second, which again, you can write it as radians per second squared, but you should try to read it as radians per second every second. That helps a little bit. Now that we have that, we can go ahead and use the summation of the torques is equal to I times alpha. And we know what alpha is. Alpha is what we just calculated. I is what we're asked to solve for. We're trying to determine the moment of inertia of this particular pulley about that particular axis. So the summation of the forces part, the left-hand side, is going to become, if you'll notice here, you could imagine a lever arm vector that points from the center of rotation to the point of application of the force. That's the actual lever arm. And you see that they're in fact perpendicular to each other. So the torque for that one is just going to be 15 newtons times the lever arm length, which is the 33 centimeters. So we're going to have 15.0 newtons times 0.330 meters, because again, you got to convert it to meters. And I'm going to consider that the positive direction. That's also consistent with what I normally do. I normally consider counterclockwise rotations positive and clockwise rotations negative. So I'm calling that a positive one, and you can see I represented it with a green vector, sort of like what we've been doing with the regular linear motion. And then I also have a torque that's applied via friction, and that's actually already given to us in the form of a torque. So I just say minus 1.10 Newton meters. In that case, that's the summation of the torques, and that's equal to I, which we're trying to solve for, times 10.0 radians per second, like that. So now all we have to do is do a computation, and we can get that by saying 15 times 0.33, and that gives me 4.95 Newton meters minus 1.10 Newton meters is equal to I times 10.0 radians per second. And 4.95 minus 1.10 gives me 3.85 Newton meters is equal to I times 10.0 radians per second, like that. And from that, we can say that I, oops, it just switched to an eraser for no good reason. I is equal to 0.385. And of course, you see a Newton meter divided by a radian per second. The radian doesn't do anything, but the second per second becomes a numerator, and a Newton times a meter is a kilogram meter squared per second squared. So it's just going to be a kilogram meter squared, which is exactly the units for the moment of inertia. Your book makes a point to tell you that this is on par with a typical 4 kilogram mass, because if it was really a 4 kilogram disk, for instance, the formula for the moment of inertia would be 1/2 mr squared. And if you take zero point 0.5 times 4 kilograms times 0.33 squared, you get about 0.2178 kilogram or meters kilogram meter squared, and 0.2178 is roughly the ballpark of 0.3875. So this does seem like a reasonable result, and that's important. I want you always to look at your result and see if that sounds reasonable. For instance, on our most recent test, in some cases, I found people thought their projectile went a few millimeters, and in other cases, they thought it went the distance that's comparable to the radius of the Earth. I try really hard not to make up physical problems or physics problems specifically that have really unrealistic numbers in it. So if you have a really unrealistic number for an answer, there's probably a reason for that, and the reason is that you didn't do it right. So make sure you keep an eye on that, just day in and day out, and not just in physics classes, but especially in the real world. I can't tell you how many times I've run into people in the engineering field or in the science fields where they get a completely obtuse answer and they're just roll with it. Just because your calculator tells you that's the answer, that is not a good reason to assume it's the answer. Anybody have any questions on that one before we go? All right, I've spaced these kind of far apart. I use basically one page per example because we're not really using paper. It doesn't matter, and I want to make sure I have plenty of room, and I hate forcing things to fit into space. So here's the next one. This is example 1011, and let me read example 1011 for you. It says, consider again the pulley in example 1010. So they're telling us to use the same pulley, so I went ahead and wrote down the information they gave us on the original pulley, as well as the 0.385 that we found for the moment of inertia. Because we're going to use that as well. But it says, consider again the pulley in example 1010, but instead of a constant 15 Newton force being exerted on the cord, we now have a bucket of weight, W equals 15.0 newtons. And of course, that implies that the mass is about 1.53 kilograms. And that bucket's hanging from the cord. See figure 1023A. We assume the cord has negligible mass and does not stretch or slip on the pulley. Calculate the angular acceleration A of the pulley and the linear acceleration A of the bucket. Assume the same frictional torque, tau friction, is equal to 1.10 Newton meters acts on the pulley. So for starters, when they tell us that the string has a negligible mass, that means we don't have to take into account the fact that as this bucket starts to fall downward, there's more and more rope on the end of it, and therefore there's more and more rope being added to the 15 newtons. But we're saying that rope is negligible compared to the 15 newtons, so we can throw that out. But they also say it does not stretch or slip on the pulley, and not stretching means that basically every little inch of rotation that the arc length on the edge of the edge of the pulley does, the string's going to move by exactly the same inch. And if it does that inch in 1 second, it's going to do the inch in 1 second on the string. And if it does 1 inch in the first second and 2 inches in the second, it's going to do 1 inch in the first second and 2 inches in the second on the string as well. So that means the acceleration of the bucket is going to be the same as the acceleration of the cord. And because it doesn't slip, that tells us that A is equal to R times alpha. So that's the critical thing that we've got to be able to use. So when we have a pulley with a rope over it and the rope doesn't slip, then that means the equations S equals R times theta, V equals R omega, and A equals R times alpha are all valid. So now let's get started. The equations we'll need, of course, are Newton's second law for rotation. That is, the summation of the torques is equal to I times alpha. These problems were mostly dealing with a single axis, so it's really more one-dimensional. That's why I'm not bothering drawing the vector symbols. In this case, though, we actually have two bodies, and the other body is not a rotating body. So that body just has a Newton's second law for it. So I had to write Newton's second law. And then, of course, we're going to use A equals R times alpha. So let's start off by looking at the diagram to the right as if it's a free body diagram for a pulley. And in that case, we get the summation of the torques is equal to I times alpha is going to give us specifically 15.0 newtons times 0.330 meters. Again, that's the exact same torque that we had before, and for the same reasons, it's just the force times the radius. And then we have minus the 1.10 Newton meter. That's the other torque, and that's equal to 0.385 kilograms meter squared, and all of that times alpha, and I'm going to call that equation one. Actually, let me not call it equation one now. Let's go ahead and do the math. And actually, I'm going to borrow the numbers I had before. Those numbers are 4.95 minus 1.10. Oops. 1.10 is equal to 0.385 kilograms meters squared times alpha, and this gives me 3.85 Newton meters is equal to 0. Oh, wait a second. Wait a second. Sorry about that. I got a big problem here. I forgot I was working a different problem. Let me restate that. Okay. We do have a force, a weight of 15 newtons hanging on it, but I can't assume that is the force that's on the other side, because if it's 15 newtons, if it's sitting perfectly still, that is a 15 newton force, and that 15 newton multiplied by 0.33 is the actual torque. But in this case, this thing's actually free to move, so all I really have is a tension. So I'm sorry I started off that way. That was really bad. Here it is, though. We're going to say the tension, which I'm just going to call T, times the radius, R0, which is 0.330 meters, minus 1.10 Newton meter is equal to 0.385 kilograms meter squared times alpha. And that was the whole reason that I took the time to borrow the other information and stuff, was because I wanted to use this equation and number it so that I could compare it with the Newton's second law equation that we're getting ready to do next. So right now, this is the actual equation we have, and I'm going to call that equation one. Now I've got a new Newton's second law for the 15 Newton mass, and we know, for instance, 15 newtons means its mass is 1.53. So we might want to take and consider the free body diagram for that. And when I do that, what you'll see is this is 1.53 kilograms it has acting on it. Now, we called the torque that caused a counterclockwise rotation, we called that positive. So what I would like to do is make a force that pulls that way positive as well. And that keeps me from having to use a negative to align A, R, and alpha. So for instance, when you use the equation A equals R times alpha, if you said acceleration, or if you said the force was positive in the torque case, but you said that same direction was negative, then your equation wouldn't be something simple like A equals R times alpha. It'd be something weird like A equals negative R times alpha. So you try to link those forces across the two different equations that way. But with that being said, what we're going to say is down on the left-hand side is a positive direction. So I'm going to say that this force right here is 15.0 newtons. And then, of course, this force right here is the tension. And for that, we have Newton's second law. The summation forces is equal to mass times acceleration. In this case, it is one-dimensional again, so I threw off the vectors. So in this case, I get 15.0 newtons minus T is equal to 1.53 kilograms times A, and that's going to be equation 2. So what we can do is solve 2 for T and plug that T into 1. So to do that, I'm going to say, okay, equation 2 implies that T is equal to 15.0 newtons minus 1.53 kilograms times A. Uh, so we could call that, for instance, 2 prime if we wanted to, but the main thing is we're going to plug that into 1. So 1 and 2 prime implies now we're going to have 15.0 newtons minus 1.53 kilograms times A times 0.330 meters minus 1.10 newton meters is equal to 0.385 kilogram meters squared times alpha. Now the big thing is it would probably be wise of us to go ahead and change that change that A into an alpha or change that alpha into an A, because then we'd have only one equation. So I can use equation 3, which is A is equal to R times alpha. And from that, we can go ahead and say that A is equal to R times alpha and plug it in. We're going to get 15.0 newtons minus 1.53 kilograms. And now in place of A, I'm going to write 0.330 meters. And then that times the alpha, like that. Put that back in the square brackets. And then we have 0.330 meters minus 1.10 newton meters is equal to 0.385. I'll leave the units off here because we're running out of space and someone else is coming in, so I want to go ahead and let them in. All right. So now we've done that, and we can go ahead and distribute terms and whatnot. And actually, it might have been better for me to have replaced that A or replace the alpha with an A, but it'll work out just fine either way. So what I'm going to do is take the 15 newtons and multiply it by 0.33 because I got to distribute that. So that's going to give me, what did we get, 4.95 last time? Yes. So that's going to be 4.95 newton meters. That takes care of this with this. And now I'm going to take 1.53 times 0.33 times 0.33, and that's going to give me minus zero, oops, wrong color, minus 0.166, and keeping an extra digit would be 7 kilogram meter squared times alpha. Okay, now that's taking care of this one with this term as well. So now I have properly distributed the 0.330 through the square brackets, and then all of this I have minus 1.10 newton meters, and then that's equal to 0.385 kilograms meter squared times alpha. So we have basically two terms with alpha in it. This left-hand side is going to become 3.85 newton meters is equal to, and now when I pull the 0.1667 over to the right-hand side, it becomes positive. So 0.1667 plus 0.385 gives me 0.5517 kilograms meter squared times alpha is the right hand side. And now I can solve for alpha, and I get alpha is equal to 3.85 newton meters divided by 0.5517 kilograms meters squared. This is the case where we can actually go ahead and add in a radian because the unit's going to come out in just reciprocal seconds squared. So I just put the radian in there, but I'm going to take 3.85 and I'm going to divide it by the 0.5517, and that gives me 6.98 meters, or excuse me, radians per second is equal to alpha. And technically, if I wanted to carry an extra digit, that's 6.978. But that's good enough. We've got this right there, right there. So there's our alpha. And now that we have our alpha, we can go ahead and solve for A using equation 3. And my pen has turned into an eraser again for no reason. So from equation 3, A is equal to R times alpha tells us that A is equal to 0.330 meters times 6.978. There's me carrying the extra digit, radians per second. So if I multiply this times 0.330, I get 2.30, and technically the next digit is 3, even though it's not a significant digit, and that gives me meters per second, and that's equal to A, the linear or tangential acceleration. Anybody have any questions on that one? So in this case, notice the actual acceleration 6.98, whereas when we had it before, the acceleration consistent with all the stuff we calculated was about 10 radians per second. This acceleration is a little less because we don't have the full 15 Newton force actually acting on the pulley. We've got a 15 Newton weight, but that 15 Newton weight is falling. So if it was actually a full 15 Newton force, then that 15 Newton weight wouldn't be falling. That's why the answers came out smaller than that. And hopefully now you understand the significant difference between the two problems. Now let's go on to example 1012. And 1012 is called rotating rod. A uniform rod of mass big M and length L can pivot freely about a hinge or pin attached to the case of a large machine, as in figure 1024. The rod is held horizontally and then released. At the moment of release, excuse me, when you are no longer exerting a force holding it up, determine A, the angular acceleration of the rod, and B, the linear acceleration of the tip of the rod. Assume the force of gravity acts at the center of mass of the rod as shown. So this is a case where we're actually not going and solving the whole thing to figure out the motion, because it turns out this equation is not necessarily trivial to solve. It would be a differential equation and that sort of thing, but we can get the initial conditions. We can basically figure out what's the acceleration as a result of this setup right now. Okay, and specifically we can figure out the angular acceleration alpha and the linear acceleration a of the tip. So let's proceed as follows. Again, we have a reference frame that is basically sitting still. So we're going to imagine our coordinate system as if the origin, for instance, would go right through the pin of that hinge there, and it's sitting perfectly still. So we don't really have to do anything with that, and we know that the Newton's second law for rotation works just fine. We know also that the moment of inertia for a rod rotated about its end per last class, which I think I did it again for my class last night. Let me double check. Is 1/3 ml squared. So when you rotate a rod about its end, the moment of inertia is 1/3 ml squared. So I can go ahead and record that I is equal to 1/3 L squared. And we're also going to make use of the fact that the summation of the torques is equal to I times alpha. Now, in this case, the only torque we have is basically the weight of the rod. So the rod is hanging or is sort of suspended horizontally. And the nature of physics is that we define the center of mass to act as the one point at which all forces acting on the object behave as the object behaves as if all those forces are acting there. So what I've done to accommodate that is I've drawn the actual force that tends to rotate that rod as if it's affixed to the center of mass. So that's the only torque acting there is the force of gravity pulling down at the center of mass. So using the summation of the torques is equal to I times alpha, we're going to get that the torque, which notice the lever arm would be the vector from the center of rotation, say, to the point of applications of the force. So this is the lever arm like that. And it doesn't really matter so much that it's a little bit above because we're pretending this, well, for one thing, we're pretending this rod is very thin anyways. That's why we're using 1/3 ml squared. So all of those being on the same line is good enough for us. But that's the actual lever arm. And you see that the length of the lever arm is L over 2. And you also see that it's at a 90-degree angle with the force. So with that in mind, oops, that was supposed to be green. With that in mind, Newton's second law for rotation becomes mg, that's the force, times L over 2, that's the lever arm, and then of course times the sine of 90 to make sure it's perpendicular, but the sine of 90 is just 1, and that's the entire torque on it. In this case, this torque is actually producing a clockwise rotation, so we could call it negative, but it's the only one, so I'm just going to treat it as positive. Why carry around a negative sign if you don't have to? Now that's equal to, since it's the only force, that's equal to the moment of inertia 1/3 ml squared times alpha. So you can see already that the m is going to cancel out with the m, and the L over here is going to cancel out with one of the L's over there, and we can solve for alpha. And in fact, alpha is going to be 3 over 2 times G over L, or excuse me, yeah, times G over L, like that. And that is the actual angular acceleration of the rod. Now we can use A equals R times alpha, which I should have written before. A is equal to R times alpha. I can use that to calculate the acceleration of the tip. So A tip is equal to L times alpha is what that becomes. And from that, we can say that A tip is equal to L times 3/2 G over L, which equals 3/2 G. And that's the acceleration of the tip of the rod. Now, that's sort of a big deal. What I want you to realize is in this case, we have an object that's sitting like this, say, and then we just allow it to fall. And what we would find is dead center right here. That would fall because that's the center of mass. That would fall, at least initially, at the rate of 9.8 meters per second per second. But at a distance twice as far away where the tip is, that's going to fall at 1.5 times G. So it's actually going to fall quite a bit later. And that's sort of one of the dangers of being around people when they're, for instance, cutting down trees. The tree, as it starts to fall, is being pulled at its center of mass, which is, roughly a little bit less than halfway up the tree because the tree gets narrower and narrower as you go up, usually. The limbs also get a little bit smaller and shorter as you go further up as well. So the center of mass is probably a little bit lower than the center of the height of the tree. And that's actually where the G would tend to make it accelerate at 9.8 meters per second per second. All that stuff above it's going to fall quite a bit faster. And if you're not careful, you could obviously get hurt. So anybody have any questions on that particular problem? All right, so now we're going to a more advanced example using calculus to calculate the moment of inertia of a thick washer-shaped hollow cylinder of mass m, inner radius r1, outer radius r2, thickness h, that has a density rho of r equal to some constant times r. What I wanted you to do is A, compute K in terms of M, R1, R2, and H, and specify its units, and then B, compute the moment of inertia for it when rotated about an axis parallel to the H and through its center of mass. Okay, now you should be able to tell what the units of K are right now. Remember, the units of rho has to be mass per unit volume or kilograms per cubic meter, and you're going to multiply K by a meter and you expect it to come out in kilograms per cubic meter. So you're going to have to say K is going to be kilograms per meters to the fourth. So that should actually be the units of K. That's something that you should always think about whenever anybody gives you a formula and it has random symbols in it. You should think, what are the units of those individual symbols going to be? So let's begin. We're going to have dm is equal to rho dv. We're going to use that. We're going to use I is equal to the integral of r squared dm. And we're going to also use that rho is equal to some constant times r. And of course, I need to go ahead and draw the object so y'all have some idea what we're talking about. Uh, that's really a pain because I did it okay, but I really didn't want it to be tilted like that, but that's what it is. Okay, let's do this instead. Okay, I'm going to try to draw it a little better from here to here. Okay, that was great, but that time it didn't automatically fix it for me. That's pretty good. And now inside of that, I'm going to have another radius or another oval like that. And then this thing is like a thick washer, so I'm going to say this height right here. And I'm just trying to draw dash lines, but this automatic program does not do very well with these little dash lines, but I think y'all can see what I'm trying to get at here. So this distance goes down here, and specifically what we're talking about is this is R1, this is R2, and this is H, and our rotation axis is going to be right here, like that. Okay, and we could go ahead and draw the axes. So this would be my x-axis, this would be my y-axis, and this would be my z-axis. Now, what I want to do is I realize that the radius is going to be in the or parallel to the xy plane and not going to have any kind of k component or z component. So the main thing is I need to make sure that my integrand, the r squared in I equals the integral of r squared dm, that integrand shouldn't change significantly from one part of the dm to another part of the dm. So I'm going to choose a differential mass element that is a thin slice. So let me show you what that thin slice is going to be. Hopefully I can use the software to make it a better drawing. So I'm going to draw around like this. And now I'm going to imagine that being just a little further out and draw another one like that. And that is going to be my differential mass element. Only you're just seeing the top of it right now. So I'm drawing these dashed lines so you can make sense of what that shape is going to be. So if you were, for instance, to lay that out, you would imagine that it's basically sort of a rectangular solid, only it's going to be a little bit less than a rectangular solid because when you cut it, the inside uh, the inside radius is a little smaller, so the length of the inside part would be 2 pi r, whereas the outside part, the length would be 2 pi parentheses r plus dr, and that's all because this distance from here to here is equal to dr. Now, in principle, what that is a cylinder of radius r plus dr with another cylinder inside of it of radius r being subtracted from it. So the real differential volume element would be the volume of a cylinder, and the cylinder volume is pi r squared times h. So what we're going to do is we're going to say pi and h are parts of both of it, but what we're going to do is we're going to have r plus dr for the outer radius, and then that's going to be squared, minus r squared for the inner radius. And what that's going to show us is it's the typical formula that you probably used in Calc 2 when you did this sort of problem in there with techniques of integration and applications of integrations. So we're going to get pi times h times, now it's r squared plus 2r dr plus dr squared minus r squared, like that. And you can see that the r squareds are going to cancel out, and that's why we have this formula that you're, again, hopefully used to from your calculus class. That formula is going to be, you'll see it in the next step, pi h times 2r dr plus dr squared. Now, we're in doing an integral, we're going to be taking the Riemann sum, which takes the limit as the differential r goes to 0. And because of that, a dr is a really, really small quantity, and therefore a dr squared is infinitesimal, and therefore we can ignore terms of the order of r squared, and what we'll get is 2 pi r dr times h plus terms of order of dr squared, which is essentially approximately 0. So that's why we normally use 2 pi RDR for just the area on top, and then we multiply it by h, and that would give the volume. So that's what we're actually using. Now, using that, I got to first figure out what the actual K is. And the way I do that is I realize they told us the total mass is M. So if I integrate dm over the entire body, then that should give me the mass M. And I can set that equal to the result and then solve for K. So that's what I'm going to do. M, oops, go back to blue. M is equal to the integral of dm, which equals, in this case, we're going to get the integral of K times R, that's the rho of R, and then times dV, and the dV is 2 pi r dr times h. So you can see automatically I get a 2 pi, a K, and an H all coming out in front. So 2 pi K H all comes out in front, and I get the integral of r squared dr from r equals 0, or excuse me, from r equals r1 to r equals r2. So that's really what we're trying to integrate. Now, if I integrate this, I'm going to get 2 pi kh times the integral of r squared is 1/3 r cubed. So I'm going to go ahead and say 1/3, and then that's going to be r2 cubed minus r1 cubed, like that. And from this, we can say m, therefore m is equal to 2 pi k, I'm going to put out here, r2 cubed minus r1 cubed times h over 3, and that gives me that k should be equal to 3m over 2 pi h times r2 cubed minus r1 cubed, like that. And that's what K is. And you'll notice that K, in fact, has units of kilograms per meter to the fourth, which is exactly what I predicted by just using the original rho equals KR equation. And I can state that by saying K in brackets is equal to kilograms meters to the fourth, and that's part of the answer for part A as well. Anybody have any questions on that part? All right. Now we're going to calculate the moment of inertia. And the moment of inertia, this is for part B, the moment of inertia is equal to I equals the integral of r squared dm. We've already figured out what dm is. Now what we're going to do is put another r squared in there. And then we're going to put the dm, which, by the way, I didn't really write this, but hopefully y'all figured it out. dm is equal to rho dv. That's what we're actually using. So now what I'm going to do is put k times r times dv, which equals the integral, or actually I'll put the k out in front, equals k times the integral of r cubed times, now we're going to use the 2 pi r h times dr, like that, and we're going to integrate again from r1 to r2. So now we've got 2 pi kh as all the constants, and I'm going to integrate from r1 to r2 of r to the fourth dr. In this case, it's going to become 1/5 r to the fifth. So I'm going to get 2 pi kh over 5 r2 to the fifth minus r1 to the fifth. Now, that has a lot of things in it that we're not supposed to have. It's got a k in it, for instance, and we're not supposed to have that. And we're normally used to just having a mass times something related to the radii, so I wouldn't expect the h to be in there either. So what we're going to do now is replace the k with the value that we know it has. So I'm going to say this is 2 pi over 5 times h times r2 to the fifth minus r1 to the fifth, and all of that is times k, and we found that k was 3m over 2 pi h r2 cubed minus r1 cubed, like that. You can see right now that the 2 pi is going to cancel out with the 2 pi there, and the h is going to cancel out with the h here. And in fact, what we're going to get is 3/5 times m times r2 to the fifth power minus r1 to the fifth power divided by r2 to the third power minus r1 to the third power, which looks just like mr squared because the top is r to the fifth and the bottom is r cubed. They cancel out unit wise to give a r squared. And that's really the only thing that's left, and that is our moment of inertia I. So that's about as nasty of an integral that you could possibly be asked to do in this class regarding moment of inertia. So does anybody have any questions on that one? All right. Your book goes over examples 10, 13, which is like a baby version of what we just did. And then it does example 1014, which is something showing us about the parallel axis theorem, but I already did one with that. But I definitely recommend you thoroughly read 1014 and 1013. 1013 because you might have been blown away a little bit by the work I did here. That whole derivation of r squared plus 2rdr plus dr squared minus r squared, uh, this whole part right here is not something you would do. I would have suspected you would have just said 2 pi r dr times h would have been dv, and that would be fine. But I wanted you to understand exactly why we can use that, because if you actually cut open that little differential mass element, it would not be an exact rectangle. It would be, like I said, a rectangle that has sort of a wedge like this because it's not quite the same size all the way across. The front of it only has a length of 2 pi r dr, or excuse me, a length of 2 pi r, and the bottom side has a length of 2 pi parentheses r plus dr. So that's why it's not exactly a rectangle, but we can pretend it's a rectangle and it gives exactly the same result, which is what we got when we said 2 pi r dr times h. That's pretending it's a rectangle whose width is 2 pi r, whose thickness is dr, and whose height is h. Any questions on that? All right, your book does do the parallel axis theorem and gives you a proof. I do expect you to know the parallel axis theorem. It then does the perpendicular axis theorem, and it does not show you a proof on that, nor am I expecting you to know that. So I think I've gotten rid of all the questions regarding perpendicular axis in the practice tests and homeworks. But if not, I'm okay with you doing them. I'm just not going to test you on it. So we're going to jump now to the next section, which is rotational kinetic energy. And really, the difference here is now, in addition to 1/2 mv squared, you can also have a 1/2 I omega squared. Remember, the rotational analog to mass is the moment of inertia I, and the rotational analog to velocity v is the angular velocity or the angular frequency omega. So it seems reasonable that k equals 1/2 mv squared should translate to k equals 1/2 I omega squared, and that's what your book shows you. Now, what we're going to do with that is we're going to use it to solve physics problems. So let's start off with example 1015. So example 1015 says flywheel. Flywheels, which are simply large rotating disks, have been suggested as a means of storing energy for solar-powered generating systems. Estimate the kinetic energy that can be stored, that can be stored in an 80,000 kilogram, 80-ton flywheel with a diameter of 10 meters, a three-story building. Assume it could hold together without flying apart due to internal stresses at 100 RPMs. So what we're told is the mass, M, is equal to 80,000 kilograms, and 1,000 kilograms is what we call a metric ton, or a thick ton, if you will, and it's about 2,200 pounds basically. Whereas the ton that we're used to in America is a regular ton, and that's about 2,000 pounds instead of 2,200. We also have a radius r is equal to 10 meters. And we're told that omega is going to be 100 revolutions per minute, and that's RPM. So we're going to, of course, use different units for that, but what we're going to need to calculate is what is the kinetic energy that could be stored in that. So we want to know K equals question mark solution. Oops. Solution K is equal to 1/2 I omega squared. Now, if this was a actual disk rolling down the road, then we'd have a 1/2 mv squared for the velocity of the center of mass as it rolls down the road. Plus, we'd have 1/2 I omega squared for the rotation rate. And if, in fact, it was rolling without slipping, then we'd have a linkage between the omega and the v in the 1/2 mv squared and the 1/2 I omega squared, such that v is equal to the radius of the disk times omega. So that's something to keep in mind. But in this case, we're just picturing a big chunk of concrete or something, 10 meters high, 3 stories high, and it's just rotating in place. So we calculate it as follows. K is equal to 1/2. Now, for a disk, a rotating disk, the moment of inertia is 1/2 mr squared. So I'm going to go ahead and put in 1/2 mr squared for I. And then for omega, I'm going to put in 100 revolutions per minute, which isn't going to give me the appropriate units. So I'm going to take one revolution and realize that is 2 pi radians. And then I'm going to realize that 1 minute is equal to 60 seconds. And then I'm going to square all that. So what I ultimately get is 1/4 mr squared times, now I'm going to take the 100 times 2 times 3.14159 divided by 60. And that's going to give me times 10.47 radians per second squared. Now I can put in the rest of the numbers. 1/4, the mass is 80,000 kilograms. The radius is 10 meters. That's going to be squared. And then times 10.47 radians per second quantity squared. That gives me 0.25 times 80,000 times 10 again times 10.47 squared, and that gives me 2.19. It looks like we're basically being given 1 sig fig and all this stuff. So me writing 3 is more than enough. And it's ambiguous as to whether it's really 2 sig figs, 1 sig fig, or 3 sig figs. Well, actually, no, it's got to be no more than 2 sig figs. So I'll put that there. But that's 2.19 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8th. And the units come out to be joules because it's a kilogram meter squared per second squared, which is a joule. So that is K for this particular problem. Anybody have any questions on that? And I got a different answer than they did. Oops, stupid me. Did anybody notice I wrote the radius was 10? They didn't say the radius was 10. They said the diameter was 10, and I wrote that. So let's correct that real quick, and then you'll get the appropriate answer. I apologize for that. So doom, D equals 10 meters implies R is equal to 5.0 meters. So if I put this in here, this would be 5.0. And now, in lieu of the 2.19, I'm basically going to have the same number. But remember that 5 was squared, so I'm going to have to divide it by 4. So divide that by 4, and that gives me 5.48. I apologize again for this. 5.48 times 10 to the 1, 2, 3, 4, 5, 6, 7 times 10 to the 7th. Joules is equal to the kinetic energy. Sorry about making that mistake, but anybody have any questions on that? Now, you could convert that to kilowatt hours if you wanted to, and your book talks about that. This energy is only about 15 kilowatt hours, so that's not a huge amount of energy. But if it's the only way to store energy, that's the way you're gonna have to do it. For instance, if you were talking about a interstellar travels, you might have, for instance, a ship that you're gonna fly in, and you want it to have gravity. So why not go ahead and spin it at a particular rate, and then you can use the normal force on the inside to act like a floor to cause the centripetal acceleration necessary to keep the objects on the inside surface and therefore giving them something like gravity. And then you could, of course, have this other main part just spinning at whatever rate you wanted to. And anytime you needed energy, you just plug into that axle, and that rotation could be used to generate electricity in whatever way you want to. All right. Now we can actually do sort of like that problem I told you a second ago when we let that rod fall. We really could only study it for that split second after it falls. We couldn't actually figure out any of the details about the motion because it would take a differential equation solution and stuff like that. But we can tell, for instance, how fast it'll be going at the bottom if we use conservation of energy. And that's what example 1016 is about. So example 1016 is called a rotating, it's called a rotating rod. A rod of mass M is pivoted on a frictionless hinge at one end as shown in figure 1030. The rod is held horizontally at rest and then released. Determine the angular velocity of the rod when it reaches a vertical position and the speed of the rod's tip at that moment. Okay, so let me draw a diagram. For starters, I'm going to say the mass of the rod is m, the length of the rod is L, and the gravitational acceleration is G. Okay, now what we're going to do is we're going to imagine the rod as being an object like this. This is the length L, like that. Oops, excuse me, that last one was a little rough. So there that is. Of course, at the midpoint would be the center of mass. And what we know is it's going to rotate about this point right here. So in principle, we can imagine that this is going to hang down to exactly the same length that it had before, which is 1, 2, 3, 4, 5, 6, 7, 8. 1, 1, 2, 3, 4, 5, 6, 7, 8 right there. So that's roughly where it'll fall to. And of course, right about here would be where the center of mass is going to fall to. And that distance, of course, is L over 2, like that. So we can use conservation of energy solution. Actually, let me write that in purple. Solution. U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. That's the version I've been using for you guys. We're ignoring air resistance and all that kind of stuff. So work in is going to be 0, work out is going to be 0, E loss is going to be 0. And in fact, we're going to take the 0 of potential energy to be in that upright position. So the final potential energy will be 0 and the initial kinetic energy will be 0. So what we have then for this is the initial potential energy is M times G times L over 2. That's the initial potential energy because we're calling this U equals 0. Okay. And then at the end, this is not actually moving. This rod is just going to rotate like that. It's not actually moving this way. So we don't have a 1/2 mv squared term. We just have a 1/2 I omega squared term. So in this case, we're going to say 1/2 I omega squared, and that omega is the angular speed we're looking for at the end, but we're asked for omega equals question mark and v equals question mark, and v is of the tip. So we're also going to make use of a is equal to r times alpha. Well, actually, no, not that. We're going to make use of the of v equals r times omega, like that. Okay. And we're going to make use of the fact that I for a rod is 1/3 ml squared. So now I can put all this in. I'm going to get mgl over 2 is equal to 1/2 times 1/2 ml squared, or excuse me, not 1/2, it's supposed to be 1/3, times 1/3 ml squared times omega squared. Now that we've plugged all that in, we can see that this is going to be independent of the mass because the mass cancels out. We can see that one of the L's is going to cancel out as well. And we can also see that this 1/2 is going to cancel out. So now our equation looks more like G is equal to 1/3 L omega squared, and that works unit wise, so that does give me some confidence that it's right. And from this, we can say that omega, the velocity, the angular velocity that it'll have at the bottom, is going to be equal to the square root of 3g over L. So that's the angular velocity. And now we can use V equals R omega to tell us that V of the tip would equal L times omega, which equals L times the square root of 3g over L. And now you can pull that L inside by squaring it, and you get 3g L squared over L. Or specifically, you can say that V tip is equal to the square root of 3GL. Now, if an object just fell that distance, you'd expect its velocity to be given by, you could use the kinematic equation that actually comes from conservation of energy, but basically what you'd be looking at is mgL over 2 is equal to 1/2 mv squared. The m's again cancel out, and the 2's again cancel out, and we'd get V is equal to the square root of G times L. So in this case, we see that the velocity is markedly larger than an object that would just fall, and that's because it has this tendency, because the acceleration, because the force of gravity is pulling on the center of mass, it tends to give it more acceleration at the tip than the middle would be. If you wanted to calculate what the middle would do, you'd find a slightly different value. But the main thing is the velocity of the tip is markedly larger than what you'd get for a normal falling body. Any questions on that one? Okay. So your book goes into section 10.9, rotational plus translational motion rolling, and it talks about rolling without slipping. That's where I told you about the S equals R times theta becoming V equals R omega when it rolls without slipping, and becoming A equals R times alpha when it rolls without slipping, or when, for instance, a rope goes over a pulley without sliding along it. And it also talks about the instantaneous axis. It says when a wheel rolls without slipping, the point of contact of the wheel with the ground is instantaneously at rest. It is sometimes useful to think of the motion of the wheel as pure rotation about this instantaneous axis passing through the point P. Points close to the ground have a small linear speed as they are close to the instantaneous axis, whereas points farther away have a greater linear speed. This can be seen in a photograph of a real rolling wheel. Spokes near the top of the wheel appear blurry because they are moving faster than those near the bottom of the wheel. So hopefully y'all have seen that before. But the big result to get out of this is total kinetic energy is equal to the kinetic energy of the center of mass plus the kinetic energy of rotation. And for that, let's work on example 1017. So example 1017, sphere rolling down an incline. What will be the speed of the center of mass of a uniform solid sphere of mass m and radius r0 when it reaches the bottom of an incline if it starts from rest at a vertical height h and rolls without slipping? See figure 1034. Assume no slipping occurs because there is plenty of static friction. Compare your results to that for an object sliding down a frictionless incline. So what we're told here is we have a mass m, we have a radius r0, we have a vertical height h, and we have we actually have an angle theta, but I don't think we're going to make use of that at all. And what we're asked to find is what will be the speed of the center of mass. So we want V center of mass equals question mark. And here's my drawing. So this is going to be the H that we're talking about. And this is the incline that we're talking about, which has an angle theta like that. And what we have is an object sitting on top of it that is a circle of radius r0 and mass m. So what we're going to use is conservation of energy. So I'm going to say solution U initial plus K initial plus work in equals U final plus K final plus work out plus E loss. Again, we're ignoring all that stuff. And this was actually kind of weird because we are ignoring friction, even though it's impossible for this to roll without slipping unless it has friction. So that's a big thing. We are going to assume that the kinetic energy is zero at the bottom. So I'm going to put, the potential energy is zero at the bottom. And it started from rest, so the initial kinetic energy is going to be zero. And we also can use, since it's rolling without slipping, we can say V is equal to R0 times omega for rolling without slipping. Okay. So what we have here is mg. Now we could actually realize that the center of mass is higher than height h. It's actually h plus r0. And if I did that, it would be in there. Actually, let me just show you because what you're going to see is it's going to cancel out on both sides. Well, I can't do it now because I said the potential energy is going to be zero. But if you said that it was the height was h plus r0, then you get mg H plus R0 on the left, and then on the right, the potential energy would be mgr0. You can see that the mgr0 on both sides would cancel out, so that's why we don't have to do that. So I'm going to say mgh is equal to, now in this case, we have kinetic energy of rotation plus kinetic energy of the center of mass. So we have 1/2 m v squared, where v is the center of mass velocity. And then we have 1/2 I omega squared for the rotational kinetic energy. And this is a solid sphere, so we also know that I for a sphere is 2/5 mr0 squared. Okay, so that's just one I've derived enough times that I remembered off the top of my head. But you would have, of course, a table of moments of inertia to use. So now I'm going to go ahead and plug in what we know. I have mgh is equal to 1/2 mv center of mass squared plus 1/2 times 2/5 mr0 squared. That's me substituting my moment of inertia I in there. And then all of that is times omega squared. Now we can go ahead and use V center of mass since it rolls without slipping. We're going to replace center of mass velocity with R0 times omega. So I'm now going to get mgh equals 1/2 m. Now in this case, I'm going to say R0 times omega, and that quantity is going to be squared. Plus, now the 1/2 times the 2/5 just gives me 1/5 m R0 squared omega squared. Now I can simplify a little bit more by combining like terms and stuff of that sort. mgh is equal to 1/2 m R0 squared omega squared plus 1/5, oops, that's 1/5 m R0 squared omega squared. So really the two terms on the right are a 1/2 plus a 1/5. The least common denominator for that is 10. So this would be 5/10 plus 2/10, and that gives me 7/10. and that's 7/10 m r0 squared omega squared like that. Now we can finally see that m times g times h is equal to 7/10 m times r0 squared times omega squared. And you can see finally that the mass is irrelevant and we can calculate what the omega is. And then once we have the omega, we can figure out the V center of mass. So oops, omega is going to be equal to 10 over 7 times G times H over R0 squared. And then I'm going to take the square root of all that. So that's the actual omega. And I can go ahead and box that off, even though we weren't asked to find that out, but that's what the quantity is. And now that we have that quantity, we can go ahead and use that to find out what the velocity of the center of mass is. And the velocity of the center of mass is equal to R0 times omega. So that's going to be R0 times the square root of 10/7 GH over R0 squared. And of course, you can bring the R0 inside of the square root by squaring it. So you get the square root of 10 GH R0 squared over R0 squared times 7. And obviously, the R0 squareds now cancel out, and we get just V, the center of mass, is equal to the square root of 10/7 GH. And you can see that's quite a bit different from if an object slid down an incline with no friction. Sliding down the incline without friction would have given me the following. Uh, MGH is equal to 1/2 big M again, M V squared, so that V would equal the square root of 2GH, like that. And you can see 10 over 7, it's, if it was 14 over 7, it'd be the square root of 2GH, but it's not 14 over 7, so it's a little smaller. So yes, we're clearly going a little slower by it rolling down the incline. Any questions on that? I will leave the conceptual example to you guys, but it's a nice one and it's something that you should definitely understand. I think it's fairly trivial to explain. I'll leave that up to you. And now what we're going to do is work out example 1019 because that's the more robust problem that I think is more critical that we get. So let's do example 1019. Still no questions on anything, anybody? All right. It says 1019, analyze analysis of a sphere on an incline using forces. So analyze the rolling sphere of example 1017 in figure 1034 in terms of forces and torques and determine the velocity VCM of the sphere's center of mass at the base of the incline and the magnitude of the friction force F friction. Okay, I'm just going to call that script F. So let's draw the diagram so we'll have some idea what we're talking about here. I'm going to draw it a little lower this time. This is going to be an angle theta. This is going to be our height h. That's going to be our angle theta. And we'll take the sphere as if it's rolling somewhere along the incline like this. That was not what I meant. Okay, so there's our sphere. And what we want to recognize is from a Newton's second law standpoint, we actually want to consider the x and y axes and all that good stuff. So what I'm going to do is I'm going to draw an x-axis pointing down the incline and a y-axis perpendicular to that. So there's my y, there's my x. Now the forces we have acting on it are, of course, this force mg, and I think I used a big M for that, so that's going to be mg. And of course, that's going to break down into components parallel and perpendicular to the x-axis. And for instance, that's going to be a negative component parallel to the y-axis. And by the way, since the angle right here is theta, this makes a right triangle. So this angle must be 90 minus theta. But this angle plus this angle gives me 90, so this angle must be theta as well. So now that we figured that out, there's our theta, and this term over here is mg cosine theta. Now, we also have a component of the mg that actually compels it to go down the incline. That term is, or that component is mg sine theta. Now, in addition to that, we have a normal force acting, and that's F sub n, the normal force. And we also, in order for this to be able to roll without slipping, we must, in fact, have a friction force acting on it. And that friction force is going to be acting right here. And I just call that F. So that's all the actual forces acting on this. And we could use, for instance, the friction force is mu static times the normal force. So solution, friction is equal to mu static times the normal force. And we also have the summation of the forces in the x direction equals mass times acceleration in the x direction. The summation forces in the y direction equals mass times acceleration in the y direction. And the summation of the torques is equal to I times alpha. In this case, we either need to treat the coordinate system as if it's rolling down the incline, and if that's the case, then we need to realize that it's an accelerating reference frame, and in an accelerating reference frame, we can only use this if we do this about the center of mass, about the center of mass, and about the center of mass. So that's key here. So now let's look at our summation of forces in the y direction. Equals mass times acceleration in y direction. Like we've done numerous times, we're assuming this thing is just rolling down the incline. That means this y coordinate shouldn't change. And since it doesn't change, that means this y velocity is zero. And since it's always zero, its y acceleration is zero. So in this case, I've got Fn, the normal force, minus mg cosine theta is equal to zero. And that tells us that the normal force is just mg cosine theta. I'm going to call that equation 1. Now I can say the summation of forces in the x direction equals mass times acceleration in the x direction. And that really is the only acceleration we're dealing with. But in this case, we've got two forces. We've got mg sine theta minus the friction force, which is mu static times Fn. And that friction force is acting in the negative direction. That's why I drew a negative. And that's all equal to m times a, the acceleration of the incline. Or excuse me, the acceleration down the incline. That'll be equation 2. We can use, of course, equation 3. And of course, equation 3 is friction force is, oh, we already used that actually. Sorry about that. I've already plugged the friction force in as mu static times the normal force, so I don't have to do that. We got that, but we haven't used equation 1, so I can combine, combine 1 and 2, and what we get is mg sine theta minus mu s times mg cosine theta is equal to ma, and we'll call this equation 3 now. So now we have an equation regarding uh, mg sine theta, mg cosine theta, all that good stuff's all in there. And that's one big Newton's second law for the whole situation. We can see, of course, that the m's are irrelevant. They're going to completely cancel out, so we don't need that. But we also have the summation of the torques as an equation that we can use. So we're going to go ahead and say the summation of the torques about the center of mass. And for this, we say the summation of the torques about the center of mass is equal to the moment of inertia about the center of mass times the alpha about the center of mass. And with this, we can look at our actual friction force, and we see that basically the mg is acting at the center of mass on the actual sphere, and the normal force is acting through the center of mass. So the lever arm for both of those are zero. So I really only get one torque, and that torque is the friction force times the radius, and it's going to actually act in a way that causes a clockwise rotation, and that's consistent with the ball rolling down the incline, which is the positive direction. So I'll keep all that positive. That's going to give me specifically the friction force F times R0 is equal to the moment of inertia of the sphere, which is 2/5 mR0 squared, times the angular acceleration about the center of mass, ACM, like that. So now I have all that, and this, for instance, can allow me to solve for just about anything I wanted, but specifically I can use it, for instance, to solve for the friction force. So, for instance, we're going to use A is equal to R0 times alpha. And let's call this equation 4, by the way. And let's say this equation right here is equation 5. And that's the rolling without slipping scenario. If I go ahead and apply that, then I would get 4 and 5 give me F times R0 is equal to 2/5 mR0 squared. But now I'm going to replace A, our alpha center of mass, with A over R0. So that's going to be A over R0 right here. That R0 is going to cancel out with this R0, and then this R0 is going to cancel out with this R0, and lo and behold, I can get that the friction force is equal to 2/5 ma, and that's the acceleration about the center of mass, basically, or of the center of mass. So that's what our friction force is. And that might be something, for instance, we'd like to know. But not only that, we can now plug that in to equation 3 if we wanted to get rid of the acceleration of mass. But the main thing is we're going to go ahead and take the friction force, which is 2/5 ma center of mass. We're going to realize that's equal to 2/5 m times. Now we're going to take the A center of mass that we got from the previous equation. Specifically, if we take equation 3, we can solve that for A. So 3 implies A is equal to G sine theta minus mu s times G cosine theta. We could do that. Uh, I don't know if that's necessarily that helpful. It does. I mean, it definitely gives me what we could use, but it's all in terms of the theta, and we can use that theta to do something as well. Let me think. Oh, I know. Because that's the problem. I substituted the formula mu sub s times the normal force in there. I could have just kept that times just the friction force. In other words, I could have just left this the friction force, and that would be kind of nice. If I go back and do that now, we can see, I'm sorry for switching boats in the middle here, but now I'm looking at 3. Let me do this with a different color so maybe it'll be easier to follow later. So if I do this, then what I'm going to have is mg, oops, I'm going to get that back. That's mg sine theta minus the friction force is equal to ma. And now I can plug in the friction force, which came from, let's call this equation 6. So now if I plug that in, I get mg sine theta minus the friction force is 2/5 ma. And then the other side, we just have ma. And therefore, we can get them on both sides. It'll be mg sine theta is equal to, now 2/5 will be added to 5/5, which is 1, and that makes 7/5 ma. And now we can again see that the m's cancel out. And with the m's canceling out, we can see that a is equal to 5/7 g sine theta. Remember, when we slide down the incline with no friction, the acceleration is g sine theta. This shows us that the friction force is actually decreasing that acceleration from g sine theta to 5/7 g sine theta. And that's not to be missed, the fact that that 5/7 has something to do with the 2/5 that the friction force is, because the friction force turns out to be 2/5 of ma. So we now have the acceleration of the center of mass, and I can't even remember what we were asked to solve. It says analyze the rolling sphere and determine, the velocity at the bottom. So we want the velocity at the bottom, and the velocity at the bottom can be given by any of our kinematic equations that are applicable, because the acceleration does appear to be a constant. And in fact, if you use using v squared equals v0 squared plus 2a x minus x0, then x minus x0 is really the distance that it rolls down the incline. And remember, the incline has a side h and an angle theta, so that sine theta is equal to h over hypotenuse, which is the distance L that we slide. So L is actually equal to h over sine theta. So with that in mind, we can say v squared is equal to v0 squared, which by the way is 0, plus 2, plus 2a times L, but L is going to be h over sine theta, like that. So we get that v at the bottom would be equal to the square root of 2ah over sine theta. But now we know that a is 5/7 g, so we can make that into 2 times 5/7 g sine theta times h, and then all of that divided by sine theta. And you can see that the sine thetas are going to cancel out like that. And ultimately, all we get is that v is equal to the square root of, all we have left is 2 times 5, which would be 10 over 7. So we get 10/7 g h, which is exactly the velocity we got before. Sorry about that. I got excited about showing you all the neat little results we could get. Actually, I should box that in red. I got excited about all the different results we could get, because we can actually learn exactly what the minimum friction force is in order to make this roll without slipping. And what we found, in fact, was the friction force was 2/5 m times a. And therefore, we could say friction force is equal to 2/5 m times, and then a we found was 5/7 g sine theta. So in this case, we see that the friction force is actually equal to 2/7 mg sine theta. 2/7 mg sine theta is the friction force. So that's just another thing we could actually find, but that's kind of interesting to know what exactly the friction force has to be to provide rolling without slipping. Anybody have any questions on that one? All right, so that was a fairly straightforward one, but because I stopped and made the friction force equal to mu static times the normal force, that made it a little more complicated. Let me just go back over what we really would have done on this had I not taken that diversion. So basically, all we did was we used the summation of forces in the x direction, summation of forces in the y direction, and the summation of the torques about the center of mass is equal to I about the center of mass times alpha about the center of mass. The summation of the forces in the y direction will allow us to determine the normal force, but we're skipping that. We don't really need that so much. But the summation of forces in the x direction gave us this, but instead of here, we would just keep that as the friction force. And the same thing here, we would just keep that as the friction force. Once we were able to figure out what the friction force was, which came from specifically the torque equation, that gave us the net torque was the normal for or the friction force times the radius is equal to specifically uh, the moment of inertia of a sphere rotated about the center, which is 2/5 mr squared times alpha. And that allowed us to supply by taking alpha as A over R0. I can put that in there, and that's going to cancel out with one of these R0s. The R0 on the other side is going to cancel out the other. So I was able to get that the friction force was, in fact, just 2/5 MA. That allowed me to plug that in here for the friction force. And when I did that, I was able to determine that the acceleration due to gravity, despite the friction, was 5/7 g sine theta. Then, once I had that acceleration, I just used a kinematic equation to because the acceleration was a constant, we were able to use that. The initial velocity is 0, and I ended up getting the same velocity we had before, 10/7 g times h to the 1/2 power, and that's exactly the quantity that we got on the previous one. Hopefully that makes some sense to you guys. Anybody have any questions on it? All right, let's try example 1020 real quick. Example 1020, a falling yo-yo. A string is wrapped around a uniform solid cylinder, something like a yo-yo, of mass m and radius r. So I have a mass m and a radius r. And the cylinder starts to fall from rest. Omega 0 is equal to 0. As the cylinder falls, find A, the acceleration of its center of mass. We want A center of mass equals question mark, and B, the tension in the string. Okay, so let me draw a diagram of that in case y'all aren't looking at your book. It'll make a little bit better sense. So what we have here is a string or a rope, if you will, that's just hanging, and from that is a yo-yo. So I'm going to draw a circle here. Let's make it a circle about this big, something like that. And the center of mass, of course, is right there. And as a free body diagram, what we do with that is we could say, again, I'm going to draw a kind of neat circle, hopefully. We could say the forces acting on this are as follows. We've got the weight of the yo-yo, mg, pulling down like that. And then in addition to that, we have a friction force, or excuse me, a tension force acting upward, and that's just plain T. And that's our free body diagram. So with this free body diagram, we can apply the summation of forces in the y direction as follows. The summation forces in the y direction equals mass times acceleration in the y direction. In that case, we're going to say T minus mg is equal to ma. Ooh. The whole thing was growing and shrinking and growing and shrinking. I thought I was having a stroke or something. Anyway, so that gives me equation one. That's the summation of forces in the y direction. Gives me T minus mg is equal to ma. I could have put it the other way as well, but this is good enough. I called up the positive direction. I called mg down the negative direction, and we do that. Uh, Now I'm going to do the summation of the torques. Now this is an accelerating reference frame because we're actually allowing it to slide down. And as long as we keep the axis at a constant direction and we do everything about the center of mass, we should be fine. So now I'm going to do the summation of the torques about the center of mass is equal to the moment of inertia about the center of mass times alpha about the center of mass. And for that particular thing, we have specifically the force of the tension in the rope is that causing the only torque. The other torque, the other force, mg, would cause a torque, except for the fact that it goes right through the center of mass, and the lever arm for that, therefore, is zero. So in this case, uh, I think, let me see, if what we know is going to happen is the object's going to, I should actually do this in the opposite direction. Yeah, let me change that direction. I'm going to say the T is in the negative direction, and I'm going to say the MG is in the positive direction, just because right now I'll have a linkage between the two, and it would require a negative sign, and I don't want to do that. So instead of saying MG or T minus MG, I'm going to say MG minus T. Same equation, I just chose a different coordinate system. In principle, I would go back and change the T to a red and the MG to a green, but we'll leave that be. Now, with that in mind, I now have a torque that's being caused by the tension in the rope, and that's tending to rotate the yo-yo clockwise. Okay, so that tension is in fact, or that torque in fact is T times R, or excuse me, T times big R, and that's the only torque that's acting. But it is in this case, we're assuming this yo-yo is like a cylinder, so the moment of inertia about its center of mass is 1/2 mr squared. So that's the I, and the alpha, of course, is just alpha about the center of mass. And that'll be equation two. So with those two equations, we can actually combine them. Basically, what I can do is I can use the fact that it's going to roll without slipping. I can use A is equal to R times alpha. Let's call that equation three. And from that, I can replace the alpha with the A over R. And in the actual torque equation, so 2 and 3 give me the following. I'm going to have T times R is equal to 1/2 mr squared, but now the A, or the alpha, is going to be A over R, so I'm going to say A over R like that. Notice the same thing's happening that happened last time. The R in the bottom is going to cancel out with one R, and the R over here is going to cancel out with the other R. So this is going to give me that T is equal to 1/2 ma. So now I know the tension is 1/2 m times A, and I can actually plug that back into equation one. Let's call this equation four. So plug 4 into 1. And doing that, I'm now going to get mg minus the tension, which is 1/2 ma, is equal to ma. Now I can pull the MA to the right and it'll become positive. Then I got MG is equal to 3/2 MA. The M's cancel out and you see, oh, excuse me, the M's cancel out and you see that A is in fact equal to 2/3 G. That's the actual acceleration of the center of mass. So I will circle that around like this, and that's the quantity we wanted. We can now find the tension in the rope as well. The tension was 1/2 MA, so T equals 1/2 MA, which equals 1/2 M times 2/3 G. So this is going to be T is equal to 1/3 mg. So that's another expression we got, and that's basically it. Anybody have any questions on that? All right. The rest of these examples are pretty good, but I think you've had quite a bit enough. In section 1010, he does a good discussion about rolling friction and stuff like that. So I highly recommend you read it. I'm probably not going to ask you any question. I'm definitely not going to ask you any questions from section 1010. But the concepts you learn are obviously important, and the concepts you learn from the other two examples that I didn't do are important as well. Does anybody have any questions before I move on? I think I'm going to jump into the next chapter a little bit. Actually, no, yeah, the next chapter is chapter 11, so I probably will. No questions on that? All right. Well, let me get you started on chapter 11 and then we'll let you go. Chapter 11 is angular momentum and general rotation. So that's what we're doing in this next part. So, chapter 11. And as I said, chapter 11 is called Angular Momentum. General rotation. Okay, so that's what this is about. And of course, it has an ice skater spinning in the air on the opening chapter. And that is the common physical principle that you've probably learned before. If you've ever seen an ice skater, she'll start spinning with her arms spread out like this, and she'll be spinning. But then as she brings her arms up over her head, reducing her moment of inertia, because remember, her moment of inertia is m times r squared. And these arms, have a center of mass out here somewhere. So that radius from her spine to there is pretty significant. But if she pulls her arms up here, then that radius goes from basically the distance from her center of her spine to her elbow to about the center of the spine to roughly maybe a little bit of an inch or two off of the spine distance. So it's decreased her moment of inertia. That decreased moment of inertia means that she'll actually speed up because it turns out L, the angular momentum, which we showed you before, was I times omega. So specifically, L is equal to the angular momentum, and that's often written as I times omega. Again, using that rotational pseudo slash axial vector scenario that we had. But if you think about angular momentum as I times omega, you can see that when her arms are spread, let's say arms wide, we have a large I and a small omega, but then arms up, where them being up means that they're a lot closer to her core. In that case, what we see is her moment of inertia decreases and the angular velocity omega increases. That is what conservation of angular momentum is. So this is conservation of angular momentum. And remember, we had Newton's second law, the summation of the forces is equal to dp dt. From this, we said if the net external force is equal to zero, then dp dt is equal to 0, and that implied p is equal to a constant. Well, guess what? We have a similar scenario here. We have the summation of the torques is equal to dl dt, which implies if the net external torque is equal to 0, then dl dt is equal to 0, which implies L is equal to a constant. And that's exactly what we saw there. That is conservation of angular momentum. I omega equals I omega. When her arms are spread wide, the I is large and the omega is small because the two have to multiply to give the same constant in both cases. When her arms are up above her or tucked in tight to her body or even down by her side, the I gets smaller, and that allows the omega to get larger because in both cases, I times omega has to be the same number. So, for instance, the left one could be something like 100 times 5, whereas this one could be, let's say, uh, let's say 5 times 100 here. That's a scenario that works. It's not necessarily that reasonable to find that our moment of inertia went from 100 kilogram meter squared to 5, but you get the point. The 5 times 100 equals 100 times 5. Anybody have any questions on that? So in this chapter, we'll be talking about section 11.1, angular momentum, objects rotating about a fixed axis. 11.2 is the vector cross product, which we've already discussed. I would like to actually compute one for you, so I'll probably do that in a second. 11.3, angular momentum of a particle. 11.4, angular momentum and torque for a system of particles, general motion. 11.5 is angular momentum and torque for a rigid object. 11.6 is conservation of angular momentum, which I just discussed. 11.7 is the spinning top and gyroscope. That is an asterisk section. There's supposed to be a KED on the end of that. It's really hard to pronounce the S, the K, and the E and the D, but that's really what it is. Uh, I'm not going to test you on that. Just leave it at that. 11.8 is rotating frames of reference and inertial forces. So this brings up, for instance, the Coriolis force. And section 11.9 is the Coriolis force. I'm not going to test you that on that either, but I highly recommend you take the opportunities to do any of the homework or any of the practice test problems that have the Coriolis force, so you'll have some experience with it. But be advised, the Coriolis quote unquote force is not really a force. Your book is calling it the Coriolis effect. Really, what it is if you actually can. The easiest way to see it is to render your coordinate system to be either a spherical or a cylindrical coordinate system, and then you imagine the r vector, the position vector, in a rotating type coordinate system. And when you do that, you have to calculate the acceleration of the r vector. And the acceleration of the r vector requires multiple chain rules. You got to use the chain rule when you're doing derivatives. So you're going to take a derivative of the r to get the velocity, then you're going to take the derivative of the velocity to get the acceleration. And one of those terms is going to look a lot like the Coriolis quote unquote force. And in fact, that is the origin of it, except you can see that you were calculating the acceleration. So it's supposed to be on the right-hand side of Newton's second law, which is the summation of forces equals mass times acceleration. Now, if you take that one term and bring it over to the left, then it looks like a force. But it really is just part of the actual acceleration written on the wrong side. So that's why there's really no such thing as a centrifugal force, nor is there anything such thing as a Coriolis force. Really, the centrifugal force is really just moment of inertia, or excuse me, the law of inertia, Galileo's law of inertia, and it doesn't actually flee the center. It just tends to go in the same direction that it was going when whatever released it, let it go. And the Coriolis force appears, even though it's not a force, it appears to deflect things to the right in the northern hemisphere and to the left in the southern hemisphere. So that's sort of the part that we're going to get from that. And it's It's responsible, for instance, for the direction that hurricane winds spiral around their center, but it's not responsible for the direction at which toilets drain and sinks drain and bathtubs drain. That's just not a large enough mass to do that, even though we've made a lot of fun videos and cartoons and stuff like that in life suggesting that that's the case. So, with that in mind, let me do a real quick cross product with actual vectors as opposed to just the symbols. And I think that'd be a decent use of my final bits of time. So, let's imagine, for instance, that the vector lever arm is going to be 2 meters I hat plus 3 meters J hat plus 5 meters K hat, like that. And I'm just making these numbers up just so we can see what they would be. And I'll show you how I go about computing them. And let's say the force that we're dealing with is going to be, let's say, 7 newtons I hat plus 11 newtons J hat plus 0 newtons K hat. So we just have a two-component force. Torque is equal to R cross F, which I've defined as the determinant of a matrix. Now, the matrix has the first row equal to I hat, J hat, and K hat. The second row is the R vector, so that's going to be 2, 3, 5. And the third row is going to be the force vector, so that's going to be 7, 11, and 0. So the way I do that is I start off with the I hat, and then I do 3 times 0 minus 5 times 11. Uh, 3 times 0 minus 5 times 11 plus J hat. Now J hat again, in this case, I am taking the J hat, and that leaves these two and these two over here. So I'm going to do 5 times 7. Notice I'm doing it in the opposite order, minus 2 times 0. So this is going to be 5 times 7 minus 2 times 0. And that's my J hat term. And now I've got the K hat term. And with the K hat term, I cover up that column and that row, and that leaves this little 2 by 2 matrix. But this one has the coefficient of positive 1 instead of negative 1 like the J did. So I'm just going to do 2 times 11 minus 3 times 7. So 2 times 11 minus 3 times 7, like that. And in this case, we're going to get 3 minus 0 is 0. 5 times 11 is 55. So that's going to be negative 55 Newton meters I hat. And then 5 times 7 is 35 minus 2 times 0 is 0. So this is going to be plus 35 Newton meters J hat. And then the K hat one is going to be 2 times 11 minus 3 times 7. So that's going to be 22 minus 21, which would be just plain 1. So that would be 1.0 Newton meters K hat. So that's the way you can go about calculating a cross product using a matrix. Hopefully that makes some sense to you. But like I said, on your equation sheet, you'll also have the formula, so you can just blindly apply that if you want. That's good enough. I think I can't go much further into chapter 11 right now. It's already bad enough that I solved so many problems in this one little interval. I know y'all are pretty exhausted, but you folks have a good weekend. I'll wait here till the last person leaves in case you have any questions. And remember, you do have a comprehensive face-to-face test during lab on Thursday, so get prepared for that. You also have an online test that you're technically supposed to do before that, and you get multiple attempts, but check what the due date is on that and make sure you get it done on time. I really advise, because the whole reason I make these online tests is to give you some practice and some confidence going into the face-to-face tests. And I give them to you every two chapters. So it's really a good thing to have done that and actually to have taken all three attempts before you take the face-to-face test. So really try to do it before that face-to-face test. But whatever the deadline is, make sure you get at least one attempt at it done prior to the deadline so that you don't get a zero for that. Thanks for coming, everybody. I'll wait for the last person to leave in case you have any questions. And have a good one. It will be, he will be taking it on paper. I have to make the copies for him tomorrow, and I'll have them on his, I'm going to give them to him at probably sometime tomorrow, or it might be the next day that I have to give them to him. But yes, he'll have it, the paper as well as printed equation sheets. You're welcome. Anybody else? How about you, Cameron? You got any questions, bud? All right. Well, he might not be here, so I'm going to go ahead and call it a day. Have a good one, everybody. Thanks for coming. Bye bye.